Hey everybody, welcome to this edition of the Microchip Livestream. As always, we're broadcasting to you live from our corporate headquarters here in Chandler, Arizona. This is your opportunity to ask a question, make a comment, or otherwise interact with us on today's topic, where we're going to be talking about creating smart signal outputs in a graphical development environment. With me in the studio, you may remember my good friend Daniel Ho.
Hey everybody.
Thanks for coming back to be with us, Daniel. Before we get started, we're going to hand things off to Matt and Wayne in the booth, and they can tell you how exactly to interact with us.
Hey, welcome everybody. It's good to see a bunch of familiar faces as well as some new ones. Welcome Jorge and Luis and Mario and Imad. Hopefully I'm saying that right. Pretty close.
You're probably not.
Probably not.
It's
probably
okay.
not, but it's okay. We'd love to see you guys all here.
It's the thought that counts.
It is the thought that counts, absolutely. Yeah, welcome everybody. We'll be basically moderating from back here as well as having a couple moderators in the chat. So hopefully if you guys have any questions, we'll either ask them live or we can answer them in the chat depending on how long the explanation is.
Yeah, absolutely. We have a super secret way of triggering our hosts that are like 30, 40 feet away from us. It's a secret Bluetooth light that's curiosity enabled.
You're breaking the fourth wall, Wayne.
Well,
we can't
you know.
do that.
It's really cool.
It is. And also, for those of you that saw, we will be giving away some great prizes this live stream to those that are participating. So in order for us to get your name into the hat, we need to see that participation. So whether that's a comment, just a shout out saying hi, a question, that'll enter your name into that drawing, and then we'll get those taken care of at the end of the live stream.
Yeah, and I think there will be 5 winners.
Five winners this time.
And you'll
yep.
get a, well, we're going to do a twofer. You're going to get actually a development kit that consists of one of our boards and a microclick. They're kind of sitting up on the table with the gentleman up there. But,
yeah. Cool.
You'll see them later.
Well, Mark, why don't you tell us a little bit more about what we'll be talking about today?
Sure. So, Daniel, this is kind of the third part in a 3-part series.
Yes.
We talked about in previous live streams, and for those of you who haven't seen the live streams, they're recorded, they're up online if you want to go back and look at those. But we talked in the first live stream about taking signals in
your MCU
from the real world and translating it somehow, whether that was digital or analog.
Yes.
The second live stream we did, which was the last live stream, we kind of talked about what you do with that information once you get it into the microcontroller.
Yes, like you can apply logic operations, you can move data without CPUs, things like that.
Right, and again, that's a good point. That's kind of the philosophy with a lot of these live streams, is that we're going to be discussing these core independent capabilities. And today is no different. So, and by core independent capabilities, and we'll look at it, we'll look at what a core independent peripheral really is a little later, and that's what we're using for most of these examples are these core independent peripherals. And by peripherals, I mean this is a feature on the chip. Today, now that we've got the information into the microcontroller, we've kind of processed the information.
Yes.
Now today we're talking about how to
Bring
actually
signal
output.
out. Yes.
And there's a few ways to do that, right?
Right.
So what we'll do is we're going to break this down into kind of 2 parts. And you know, these are just two different scenarios that we came up with. I'm sure.
Yeah, there are a lot of scenarios,
Yeah,
but
there's a lot
I
of different
mean,
ways.
coming from like toggle and IO pin to all the way to like driving MOSFET or sending out the signal.
Yeah.
There's all kinds of outputs.
So outputs, you're going to be driving motors, you're going to be doing moving actuators, maybe even it's as simple as lighting an LED or sending information to an LCD or a communication. And we'll cover a few of those.
Yes.
So what we'll do is we'll break this down into 2 parts. The first part is we're going to actually output to drive something. So as I said, there's the motors, you have LEDs, that kind of thing. So Daniel, the one thing that we wanted to make sure we talked about in this live stream was our input-output ports.
Right.
And these are something that is on literally every microcontroller you could possibly imagine. But
Mm-hmm.
Microchip's 8-bit devices that we're going to talk about today actually have some unique characteristics associated with the general purpose I/O ports.
Right, exactly.
Can you talk a little bit about that?
Yes. If you guys can switch to my screen, actually, if you think about the I/O capabilities, there are actually essentially two things you care about, right? One thing is if you toggle I/O pin, the speed you're toggling it,
Okay.
or you're driving it, and it's pretty much determined by the current, because if you're driving a FET, the speed, the amount of the current is depending on your speed to drive the FET.
And why would you drive a FET? Like what for newer users? Why would you drive a FET?
So I mean, MOSFET is widely used in all kinds of like embedded system designs where you essentially use that as sort of a switch.
A switch, yeah.
Yes, and we have like 4 MOSFET together to form what we call the full bridge to drive things like motors.
Okay.
Yes.
So essentially, you're controlling where current or voltage is inside of a system.
Yes.
And that's what you're doing when you're
Yes.
essentially
I mean,
driving
if you're
a FET.
driving something with I/O, the two things is current and voltage. Like how much voltage can you reach to drive something.
Okay. And the majority of applications that are out there use general purpose input-output, or
Yes.
as we
Yeah.
short form it and call it
Yeah,
GPIO.
Exactly. I've visited a lot of customers. They just use our PIC or AVRs to just do simple GPIO control.
And you can get down into very tiny devices if that's
Yes.
all you need.
Right.
Okay.
And sometimes that's all you need.
Right.
Yeah.
Okay. So let's talk about some of the capabilities on these I/O that we can talk about with our customers who are watching.
Okay.
Hopefully, customers that are watching.
Yeah, so as we spoke, there are two things, current and voltage. Speaking of current, the things I can think of is the high current I/O pins we have in our devices. And I mean, I can think of many ways to demonstrate this, but I think the most straightforward way to show the specs here.
And
So
this is the specs you grab from the data sheet.
Yes.
Every data sheet will have this at the back end of the electrical specification. This
So
is actually the first page of that section.
Right, and so this is the spec for one of our devices called PIC 16F1619, and it has the high current I/O PIC capability. So most standard I/O pins we can drive up to 50 milliamps, which is already like a lot compared to others.
So, and in some instances, these are being touted as high current
Yes,
I/O.
it's already
15,
called,
20,
yeah.
25 milliamps.
But right now it's all in our standard, like our new devices are all in our standard I/Os. But I want to make sure, like, you should keep in mind this is like the absolute max value.
Right.
So in your real design, you probably don't want to reach that kind of level.
Yeah, you run any device at its listed
Yeah.
current for too long at its max current, and you're bound to damage something.
I usually run at like half of it.
50%, yeah.
Yeah.
Okay.
Yeah. And we also have this high current I/O, which can reach up to 100 milliamps, which is pretty amazing.
That's high, yeah.
Yes.
And so what impact does this have on my application? Why do I care about this?
So there's two things I can think of. One is, say I have an example when I was using a device before and I need to drive something called a triac. You can
Okay.
think of it as a switch. So in order to turn on that switch, you need a relatively high current.
Okay.
And what I had to do is I actually route 2 pins together to drive one switch.
This was your solution without this high current I/O.
Yes, and I mean that's widely used in a lot of designs.
Okay.
Like people do that; they route 2 pins together to drive one
Okay.
output, and then now I have this high current I/O where I can just use one I/O to drive the thing. So I'm
Okay.
saving one I/O.
Oh, very cool.
Yes. Another thing is, as I mentioned, the switching speed. Sorry. Like if you're driving a MOSFET,
Okay.
the higher the current is, the faster the FET is going to turn on.
And like you said, MOSFETs are used widely as switches in the systems. They're used widely as things for motor control, lighting. These are just things to keep in mind if you've heard of H bridges or half bridges, that kind of thing. I think we have a question in the booth, Matt?
Hey, yeah, Mark, thank you. So we have a question from Kumara, and it's, so 50 milliamps is super. Is it the same across all PICs? So do every PIC device have that 50 milliamp option, or is that only on certain devices?
So I would say a lot of our, like most of our new devices have
Right.
50 milliamps. So I can go online. So today we're going to use this board called the,
Let me switch back over to
yeah.
you. Otherwise, they're just looking at us, smiling.
Right.
There
So
you go.
this is also our giveaway, is this Express board, which is using our device called PIC16F18855. And if I go online to the data sheet,
Very riveting.
yeah.
By the way, while you're going to the data sheet, Mona says hi.
Oh, hi, Moon.
Actually, she said it's great to see. What did she say? Great to see an outstanding young engineer
Exactly.
like Daniel.
Exactly.
I'm
No
pretty
mention-
much sure she means Mark.
Oh, I don't know.
No,
about
no
that.
mention of Mark.
Hey, I also want to give a quick shout out to, I think I'm saying this right, Gerard, but I've seen you at a couple live streams now, so it's cool to see you back again. Welcome back.
Howdy.
We've also got Craig Potter from South Africa, and Jasper's joining us from Nigeria. That's pretty amazing.
It is.
Wow.
That's awesome. Welcome, Jasper. Yeah, great question, Kumar. Do we have that data sheet up
Yeah,
now?
it's up.
Yes.
Awesome.
Okay, cool. Let me, there we go.
So I've pulled up the data sheet.
And if you want the data sheet, they didn't see you actually navigating for it, but all you have to do is type into your web browser, www.microchip.com/the part number, and that'll bring you right to the product homepage. And then down a little bit, you'll see a Documents tab, and you just click on that, and it'll bring you to the data sheet.
Yeah. So as I said, I opened up the data sheet of our device 1855. It's a regular device, but it's a relatively new device, and you can see, I know the text is kind of small, but the standard I/O pin is 50 milliamps.
50 milliamps.
Yes.
Now, like you said, this is on newer products. I mean, if you go back to some older products, you'll notice that the I/O current that you can sync or source is probably around 25 milliamps,
Yeah.
20 milliamps.
So it's
And this
still
includes
kind of
AVRs
high.
as well, not
Yeah.
just PICs. That's one of the things with these devices, is the ability to actually source this large amount of current and sync. And that kind of brings up the next point. If you're syncing current, this next point might be something of relevance, where we're talking about the ability to do open drain.
Yes.
And what does that mean to us?
So before we talk about open drain, we can use that as an output and basically put your supply voltage higher than your PIC VDD.
Okay.
And so I'm gonna show you a
And
picture.
VDD is what? The VDD.
It's the supply voltage of your microcontroller.
So that's usually that's the maximum output that you can do.
Yes.
Unless you have like some sort of LDO or something
Yes.
that's on your microcontroller.
Yes.
Okay. So let's, if we can take a look at Daniel's screen, he's going to
Yes.
go through a.
So what I'm showing to you guys is a regular digital output where we just use the I/O pin as a digital output to drive, say there's an LED there.
Okay.
And then you can see the VDD is the supply voltage of our MCU. And in this case, it can be up as high as 5 volts. I mean, 5 volts is already like higher than a lot of other MCUs.
And that's written to like a port. And if you, a port register, and if you set the bit in that port
Yes.
register, you're driving that output pin high.
Right.
And that's the high, quote unquote, is going to be your VDD plus or minus a little bit of voltage. And
Yes.
that's also detailed in the electrical specs.
Right.
There's some protection diodes in there to make sure
Yeah.
bad things don't happen. But
Right. But I'm just showing the main part of this I/O pin
Yes.
driver, which contains 2 FETs.
Okay.
And it's what we call the push-pull operation.
Okay.
And then for the open drain, basically I'm blocking the upper part of the circuitry where you only have one FET, one N FET, and then you drive that FET just as a regular FET. So you can connect it to an external voltage
Okay.
higher than your VDD.
So what that allows you to do then is to, instead of having that VDD plus or minus, or VDD minus that certain amount, you're actually able to drive 12 volts at that point, or
Yes.
whatever the specification would be.
Right.
So what would be your limitation on that voltage? I'm going to assume that it has something to do with the amount of current you can sink.
Yes.
Correct?
Yes.
Okay.
And also, like, well, if you check the spec of your FET in the I/O driver, then you will know what kind of voltage can you
Okay.
drive up to.
And I'm assuming that you had a resistor connected into the pin that also provides like a current limitation.
Right.
So,
And I also have a pull-up resistor there.
because we have some parts that are considered high voltage parts that you can actually connect to a higher voltage than, say, 5 volts
Right.
or 3.3 volts.
Yes.
But that is all going to be, and people ask, well, how high of a voltage can I run? And that's all going to depend on the resistor that you choose, right? Because the resistor is going to limit the amount of current that goes into your device, and how much you pay for that resistor, how much is your dissipation on that resistor that you can do, the power dissipation. So there's all sorts of little variants, but the electrical specs in a data sheet are very important whenever you're making these types of choices.
Yeah.
Okay, cool. So another thing that we want to make sure we mention is peripheral pin select. Can you talk a little bit about that?
Yes. So the peripheral pin select is basically giving you an option to make your digital pin really like flexible.
Okay.
Like basically in our PIC devices, you can route your signal to any digital pins you want to, and even like multiple digital pins.
Okay.
And when you do that, basically when you design your layout, say for your chips, or like if you want to upgrade your design from one MCU to another MCU,
Okay.
you don't need to modify that layout a
So
lot.
much, yeah.
Yeah.
I think another nice feature too is just if you're routing signals around a new application, it kind of minimizes the amount of tricky routing of the traces.
Right.
I mean, because as soon as you add a trace to a board, you're adding one of a few things. You're
Yes.
either adding a resistor, a capacitor,
Inductance.
an inductor,
Yes.
or even an antenna, depending on
Right,
certain
right.
situations.
So the way you route your circuit on your board, the way you lay out your board is really important.
Oh
sometimes.
yeah, of course.
Yeah.
Okay. So that's kind of the general purpose I/O. And we have some other capabilities that we're not talking about today. But I mean, if you go into the data sheet on this particular device, the 18855, which is on these boards that we're giving away, you'll see other things like slew rate control, and there's a description of what that does. There's pull-up resistors that you can apply to the pin to help reduce external components and so on. So the point is, general purpose I/O is just not a basic input-output. There's so much more to it.
Yes.
Okay. All right, so that kind of covers the I/O aspect of it. Let's talk about another capability. Let's talk about a new peripheral that is in recent years called the Complementary Waveform Generator.
Yes.
Can we do that?
Of course.
Okay,
So
let's do it.
After talking about driving the I/O, then we talk about actually driving something like a motor or
Okay.
a power supply, and usually it involves in kind of sort of like a PWM output,
And a PWM, for those who don't know, is
Pulse-Width Modulation.
which is a square wave. So it's
Yes.
it's on, off, on, off, on, off, if you're thinking about it in a digital I/O.
Right.
I think we have a question in the booth.
Hey, Mark. Yes. So we had a question from Jorge, who I believe came out to one of our effortless design things a couple weeks ago.
It's the Jorge Amadeo. Yes.
The Jorge Amadeo. Well, Jorge, it's good to see you. It's good to see you logged on. That is a great side tangent that we do have these effortless design classes that run around the U.S. and I guess internationally a little bit as well.
Well, we haven't taken the show that far on the road yet, but we are planning on doing some international
Yeah.
over
So
time.
if you want to check that out, if you go to microchip.com /
Effortless design.
effortless design. Yeah. Cool.
Put me on the spot there.
But the question is there going to be are there other Express boards for different parts like the PIC 18?
That's an easy one for you.
Yeah, if you go to microchip.com/express, or even a product homepage, you should be able to find a link to express boards for a variety of our parts, including PIC18 devices. That's kind of new products moving forward are going to have these express boards. Now, they're not going to be in this format with the green board that we have here is kind of a unique beast in that it has a push buttons, it's got a pod on it, it's got
so it got this
some
header
LEDs.
for the
It's got a header
click
for the
boards,
clicks and so on. The newer express boards are going to be basically just a chip that has been populated onto a tiny board that is almost the size of a piece of gum. You know, a bigger piece of gum, maybe not the little guys like that, but maybe like the thinner gum.
Yeah.
That's all they sold when I was a kid. But that and chiclets.
Back in the olden days.
Back in the olden
That's
times.
true. You guys
when
don't
everything
know
was in
how
black and
well
white.
you have it with gum, you younger people.
We'd drive our dinosaurs to the store and buy our gum. It was pretty cool.
I've heard of it.
Yeah. But yeah, so most of those boards, and they've been designed to have a programmer on it, to be able to actually go right into your application if you want, and then solder it in. It's kind of the footprint of a PDIP, if you're familiar with that style of packaging. So yeah, we do have many options for express boards. If you need the capabilities that this particular express board has, you'll have to get this particular express board with the 18855 on it.
Or a Curiosity.
Or a Curiosity board, yeah, that's another nice development platform where you can actually take PDIP devices and swap them out, so you can
So any
have one
devices
board.
you can use it. Yeah.
Cool.
Thank you, guys.
Well, thanks, Mark.
Okay.
Cool.
So complementary waveform generator.
Right. So this peripheral is pretty flexible for a lot of driving things. I'm going to show you some of its modes, and you will understand. Like this is push-pull mode, which is essentially used for like driving sort of like a power converter or a transformer. So this is how you usually drive an inductor.
So this peripheral allows you to take a single PWM source or a single square wave source and then run it through this peripheral, and then you've created a complement of that input waveform.
Right.
So you can see output A is one waveform, and its complement is output B.
So basically it's applying their customized timing or logic to your waveform input to make this complex waveform output. And like this mode is basically for driving things like a brush DC motor, where you can directly just hook the motor into this full bridge and just route the 4 pins of the CWG output to the 4 FETs, and then it's going to have this mode.
And that's a good point. And on this diagram, we've kind of high-leveled it a bit, but those circles, the Qs, are actually MOSFETs.
Yeah.
And on the top, you probably have P channel, and on the bottom end of the H bridge, you probably have N channel MOSFETs.
Yes.
But that's very common configuration for driving a DC motor bidirectionally.
Yes.
Or if you want to do a stepper motor, that kind of thing.
Right.
Okay, cool.
And also it has the half bridge mode, which is doing the actual complementary output.
Okay.
What we mean complementary is the lower bridge of your output is exactly opposite of your higher bridge.
Okay.
And usually it's also for driving sort of like a half bridge circuitry.
Okay.
But normally if you want to drive that, somebody says, okay, I can just invert my PWM to do it, right?
Right.
It's the same thing, but actually it's not, because there are some timing issues here. If you switch your 2 PWMs together, it's going to be sometimes that they're on together.
At the same time?
Yes.
Even if it's for microseconds or... Okay.
Yeah, just a little bit of time is going to create this current shoot-through from your power supply to all the way to your ground.
And what does that do?
Well, that's going to hurt you a lot.
Yeah.
I mean, not you, but the FETs.
Okay,
Yeah.
so you're probably going to, I mean, if you're familiar with current, it's voltage divided by resistance, and if you don't have resistance
Your
or that
current-
much resistance,
yeah.
the closer you get
Theoretically,
to
your
zero,
current is-
your current can go through the roof
Yes.
and just damage your parts, your motor, even your MOSFETs, your microcontroller, and so on.
Yes.
So
the solution to that is to insert what we call a deadband. And the CWG can insert this deadband control automatically for you. So you can configure the CWG to set the rising edge and falling edge deadband time.
So it's basically creating a bit of a delay
Yes.
between those two edges to ensure that those those signals don't turn the MOSFETs on at the same
Exactly.
time. Okay.
Yeah.
Very cool. And that's part of the hardware. And you know, traditionally to do this, you would have needed some either a piece of code to do
Yeah.
this, or some external components like some resistors, some capacitors, and
Right.
that kind of thing.
Yeah.
So, okay.
If you're using code, it's a big piece of code, I would assume.
Yeah, I
Yeah.
would assume so too. And that's the whole point with our core independent peripherals, or with peripherals in general. It just gets rid of the need for you to write code to do something. So
Yes.
this peripheral integrates these capabilities in there.
Right.
Now, there's kind of another piece of this which you could say is the auto shutdown capability. And what does that do?
So basically it does is, so we're talking about functional safety these days a lot, right? So I would say this feature is perfect for the functional safety, where if you're running either a power supply or a motor or something else, and you say, for example, you monitor a overcurrent through your comparator or some I/O pins, and then you feed that signal back to your CWG. It has a auto shutdown input, where if your signal is turned high, it's going to be auto shutdown your PWM output.
Okay. So, and I've seen applications where they've used these devices with this feedback loop that reads over current into something like the CWG,
Right.
shutting it off. You have another signal that can turn it back on, and then this is a self-sustaining system.
Yes.
As long as your desire for that motor speed or brightness of this LED, because it's not just for motors.
Yes,
This
exactly.
I've seen this on
Yeah.
power supplies, all sorts of different applications. But you can actually connect all of this together in such a fashion that it operates independent of the central processing unit.
Yes, and
The
I
core
was,
where your code is running.
yeah, and I would say as long as you're designing your design to drive something, ideally you should have this current protection somewhere in your circuit.
Yeah, yeah,
And
for sure.
your MCU has this hardware capability of determining whether to shut down your PWM, then you're good.
Okay, so next on this is this. Are we doing the demo, or are we going to?
Oh, we're gonna talk about the NCO first.
Oh, you want to talk about the? Okay,
Yeah.
good point. Because the demo uses the NCO.
Right.
So what is the NCO? It's
So-
numerically controlled
Yeah, as
oscillator.
it sounds, it's a numerically controlled oscillator. It can output a dynamic frequency
Okay.
range. You can either use that as a clock or a driving signal. And we're gonna demonstrate this part. So let's do the demo first then.
Okay. So
So it's gonna be a little bit loud, I would say.
well,
So-
depending on where you are. If you're
Yeah.
here, it might be loud. If
Right.
you're out there in YouTube land, it's probably not so loud.
So we're using this buzz click, which is essentially a buzzer.
And how are you driving that? That's going to
So
be.
I'm going to use the NCO, but we're
But
going
it's
to
a
come back.
PWM, right?
It's a PWM.
Yeah,
Yeah.
so-
yeah. It's a
okay.
square wave basically,
Okay.
and we're going to change the frequency from low to high. So you're going to hear the tone from.
And how do you change that tone? It's you
Basically, change the frequency of your
Okay.
square wave.
And that's important to remember for when we talk about this peripheral.
Yes. So I'm going to plug it in. If you guys can hear me, it's a frequency sweep. So it's from low frequency to high frequency, and the
Okay.
tune become from lower to higher. Yeah.
Okay. And so that kind of capability, where would you use that other than this little clipboard here?
Well, it's being used for a lot of applications where it's include like audio or driving something simply.
Okay.
Yeah, it's not only the buzzer.
Okay.
Sure.
So let's talk a bit about the numerically controlled oscillator and why do I care this thing exists?
Yes, and as you mentioned, it's essentially a PWM. So
Right.
let's take a look at the PWM first.
Okay.
So the PWM is basically pulse-width modulation, where if you think about the PWM, it has two things you need to care about. One is your timer source, which your PWM going to use the timer as your input source, and the timer determines your period of your PWM.
Okay.
So as long as you have the period, the next thing you want to care is the duty cycle,
Which is one of the most important parts.
yes, which is it's essentially on time.
Yeah.
So you're going to have a timer source which determines your period, and if you have a duty cycle counter which determines your T on, your on time.
Okay.
And then usually how you use the PWM is just to change your period stays the same.
Yeah.
Basically, that's how PWM is usually used, and you adjust the on time to make the change of your PWM duty
Okay.
cycle. So what if I'm going to do something like what I showed in the demo, where you actually want the duty cycle stays the same, but you want to change the timer period?
Okay.
Then you got to change two things in your PWM now. First, you're going to change your timer source to longer, and then you're going to change your duty cycle source.
Okay.
So these are the two parameters, and you need to keep counting or keep calculating on either the prescaler, your timer source, all kind of elements comes in here regarding to producing this kind of signal.
Because since everything's based off this timer, if you want to change the frequency, you now have to, in every data sheet, you're going to have inside of that PWM section,
Yeah.
you're going to have some equations that you have to do to,
Right.
so if you change your frequency, that affects how your duty cycle looks, because that, when you boil it right down, you're writing values to registers
Yes.
at some point.
Exactly.
Whether you're using a tool or whatever.
I'm going to show a flow chart
Okay.
after that
Okay.
to show the calculation using the PWM.
Okay.
But if you're using the NCO, it's a different story, because the NCO can do a 50% duty cycle output, which is essentially a square wave with a dynamic change of your frequency. So with NCO, all you need to change is the NCO accumulator, which is just one element here to change the period or the frequency dynamically.
And the way the NCO is set up, one of the modes is fixed duty cycle mode.
Yes.
So it's going to keep you, that fixed duty cycle mode keeps you at 50%.
Right.
So by using the PWM, it looks like this kid's pretty frustrated.
Yes.
But if he's doing now, if you're changing the duty cycle, that's fine.
Yeah.
I mean, you don't have to go through this, but the period, this is what you'd have to do.
Yeah, I mean, PWM has its usefulness in a lot of things, but sometimes you need that precise frequency control to your
Right.
output.
And it's not
the
just-
NCO is 20 bits.
Yeah,
and it's
20 bits resolution.
Yeah, it's higher than most.
And that's a good point. If you're using a PWM, when you're dealing with the resolution, what that's saying is how, so the duty cycle is how long that output is high and then how long it's low. And the higher the resolution means, so if it's an 8-bit, that's 250 different duty cycles you can have within
Yeah.
that period.
Yeah.
However, that's very dependent on your clock speed. So if
Right.
your clock speed is slower, that reduces that resolution.
Yes.
It's just the nature of the beast, right? I think we have a question in the booth.
Hey, Mark. Yes. So we have a question from Craig Potter.
Okay.
And he was asking, can MCC create the interface functions to simplify the NCO, the PWM, even going back to the CWG as well?
Yeah,
That's a really, really good
That's a
question,
good
because we're going to
segue,
show
yeah.
that in a minute.
That's
yeah.
totally why we asked it.
Yeah.
yeah.
Okay.
See,
so,
we're professionals back here in the booth.
Yeah. So,
so let's just open up MCC. So this project is created by my colleague to drive that buzzer click. And then if I go to the MCC, I don't know if you guys can hear, I mean, I see it really,
can you zoom in?
yeah, I cannot really zoom in.
And by the way, MCC, for those of you who don't know, all of you should know, MPLAB Code Configurator.
Yes.
Yeah, and that's just, you know, with all these peripherals that we're putting out, and there's a lot of them,
Yes.
and not all of them are standard across the entire industry. You're going to want to take these peripherals out for a test drive, and this tool just kind of abstracts things for you, so it gives you a high-level view of what this peripheral looks like.
Yes.
So you don't have to go in and start pinging registers and writing intense software routines to make this happen.
Yeah, like this graphical tool is pretty obvious to me. Like I can select the fixed duty cycle mode here, or there's another mode called pulse frequency mode,
Okay.
which is you can set the on time to be this much of a clock.
Okay.
And then we're using the fixed duty cycle mode, and what you need to do is select the clock source here. And what's neat about MCC is you can just type in any kind of frequency, and it's going to calculate your on time, off time, and it's going to calculate your register output for you.
And this isn't an insignificant thing. I mean, this is something that you would have to calculate yourself.
Mm-hmm.
You would spend time on. Maybe you miscalculated something.
Yes.
And then you have to go back and debug that. I heard an interesting quote in a paper I was reading the other day. If you want to get rid of human error in an application, you have to eliminate humans building the application. So that ain't going to happen.
What
Yeah.
were you
So-
reading?
Yeah.
But
exactly.
that's I mean, everyone makes mistakes. Everyone's code is never perfect the first time.
Exactly.
And this kind of minimizes that development cycle.
Mm-hmm.
Okay, cool.
And if I want to show the PWM, it's also really simple. Like, I can just go to the device resource, add the PWM. If you can switch to my screen here.
And if you joined us for previous live streams, you'll know that the code configurator is actually free. You can add it as a plugin into your MPLAB X integrated development environment, which Daniel's using here to build the code.
Yeah.
And you can get more information at microchip.com/MCC. There's videos, there's all sorts of things.
So if you look at my monitor right now, I'm configuring the PWM. And first thing you need to do is configure your timer resource here. And it's really easy here. Like if you can change the prescaler, MCC is gonna calculate the upper limit and lower limit of your period here. And you can put anything you want within that period. It's gonna calculate, this is the actual period here. If you cannot see it, it says 9.9 instead of 10 because of the resolution of your clock and everything.
And your duty cycle
Yes.
is?
So I switch back to PWM, I can determine the duty cycle here.
So how long in that period do you want that output
Yes.
to go high?
Yes.
50% of that
Anything-
period?
Yeah, and it's going to calculate your register output for you. And
There's your resolution.
if you note there's a resolution here, as Mark mentioned, this is a 10-bit PWM, but right now I'm using 9-bit resolution just because my timer and prescaler and everything is determining my resolution, not only the PWM.
And this is where the NCO comes in with its 20-bit resolution, and not only that, but with the calculations that you'd have to do in code, because once your microcontroller is running, it can't just open MCC and go back and reconfigure things. You'll have to put some code in there.
Yes, and here is the CWG, where you can select multiple input for your signal, and there's steering mode, push-pull, half bridge, full bridge. You can
Nice.
select that.
While you're actually in MCC, do you mind sharing the pull down for clock options for the NCO? We have a question
Okay.
on those.
Yeah, no, we had a question a little bit ago that I think is actually really important, not to take us back too far, but this is, I think, a pretty short answer. Somebody who's clearly been around for a while was asking, is CWG the same as the ECCP on the PIC-18F devices?
Yeah, so
Pretty similar.
And not just the PIC-18F, but the PIC-16F, the PIC-10Fs. So ECCP was kind of, it was aspects of the CWG added onto a PWM generator. But what happened is that we found some customers wanted to have some of that capability, the bridge modes, the complementary drives, the deadband delay, those kind of capabilities, but they wanted to be able to run different sources in there. So maybe an analog signal source,
Yes.
maybe another clock source, but regardless, it's kind of aspects of the ECCP, which stands for enhanced, capture, compare, PWM, and the enhancement added the bridge modes. But this added bridge modes that you could actually access from almost any signal in the microcontroller.
Yes, so it gives you more flexibility in your design.
Absolutely.
Yeah.
Cool.
Cool.
Thanks, Mark.
Okay.
Yep. And so where were we at?
Clock
the
options.
NCO, yes, the NCO clock option. So you can see there's FOSC, which is your main clock. You can switch to the high frequency internal oscillator, where you can keep the NCO, keep the high frequency internal oscillator running during a sleep.
Sleep mode, yeah.
Yes.
So there's certain, so for those of you who don't know what sleep mode is just a low power mode where you're essentially turning off the central processing unit, you're turning off a lot of the features on the device because you want to put this into the lowest power consuming mode. In fact, most applications, you're going to want to run your application, especially battery applications, 99% of the time in this low power sleep mode. So the idea is to conserve battery power if you're doing something like energy harvesting, that kind of thing.
Yes.
And this just gives you another capability that you can run in this lower power mode to keep it as battery friendly as possible.
Yeah. And if you look at the other clock source on my screen here, if you're not familiar with the name, that's actually the CLC output. So I
configurable logic
remember
cell.
we talked about the CLC last time.
episode, yeah.
It's a logical output, so you can have all kinds of logical output feed into your NCO as your NCO clock, and that adds flexibility to your design.
And create maybe a unique peripheral, kind of like what we're going to talk about in the next section. So just having these two parts. So the first part, we wanted to drive something. So we talked about general purpose I/O, we talked about PWM waveforms, square waves, that kind of thing, improving the resolution.
Yes.
The second part we're going to talk about is just the ability to output digital signals to communicate with another chip, or like a communication implementation. So can we talk a little bit about, on the 18855, this product here, what kind of communication peripherals do we have on this?
The three main common communication protocols are all implemented as a peripheral in our 18855. They are I2C, SPI, and UART.
And a little bit about each one of those. I2C, kind of a two-wire communication.
Yes.
The one wire is data, the other is a clock. And so you can use this to communicate with what usually?
Say a digital sensor, or you're outputting your command to another driver chip or something else.
And so like on this board, as a matter of fact, you're going to, there's an I2C temperature sensor, and there's examples on our Xpress website. Again, that's microchip.com/Xpress. And if you go to the example section, you'll be able to find like a temperature sensor.
Yeah.
And this uses this I2C, one of Microchip's I2C temp sensors.
Yes.
So the SPI, similar situation. Some of our sensors.
They're all like data protocols. It's like a language we speak. Like I talk to you, we both speak English, and then we can understand each other.
Right.
If I start speak Mandarin here, and then you
I wouldn't understand a word. So the other aspect of this is the EUSART. So EUSART, now customers or viewers may be familiar with a UART, which is essentially a serial communication.
Yes.
But how does, and that communication protocol is used for many things, including sensors.
Yes.
Including Microchip sells a bunch of different wireless modules, Bluetooth, low energy, Bluetooth, Wi-Fi, and these all connect over, a lot of them over UART.
Yeah.
But this particular peripheral says it's EUSART. So what does that mean?
So there's an E and S add to it, basically.
Yes.
So UART is a asynchronous communication where, say, I have a baud rate I'm running.
Okay.
So I have a rate I'm transferring data, and you have another rate. And you're going to assume that we have the same rate to communicate to each other. That's asynchronous communicating. Where the USART, where the S means is a synchronous where we actually share a clock. So I know it for sure that you're transmitting the data at the same data rate as I am.
And just the importance of that. I mean, if you're doing an asynchronous communication like that, and you have, say, 2 microcontrollers, and that's a possible implementation of this, 2 microcontrollers communicating over a UART, you have to have very accurate clocks on both devices, which can increase your cost, and also demand like a little more power maybe.
Yes.
But you are...
and also, like if you have a synchronous implementation, you can run the
where
data
if they're
way
sharing
faster.
the clock line, I mean, even if the one clock doesn't have a lot of resolution or you know, tolerance to it, you're still sharing that clock. So whenever the clock goes high, like a PWM or a square wave, it's going to go high on the line, and both devices are going to recognize that as a clock transition.
Yes.
That's an over elaborate explanation of a simple thing, but okay. So now the enhanced part of this, what does that mean?
So the enhanced basically means we add the capability of driving a link protocol on the UART. So the link is another data transfer protocol. Basically, they are widely used in all of the automotive applications, where in cars you use link to be the data transfer.
And there's also the ability to do RS-485 on this, IRDA. The enhanced, I guess, just means it's added additional functionality to a fairly standard peripheral. But again, if you were using just a basic UART, you would have to write like a wrapper around this peripheral in software to implement some of these protocols.
Exactly.
And this simplifies it, including there's lighting protocols on some of our parts, like Dolly DMX. So check that out. So that's the implementation there. So if we carry on this path, those are common protocols.
Exactly.
There's a body that says, hey, I squared C SPI follows this protocol. If you're going to make a device with this on here, you're going to follow this set of rules. Everyone agrees on this. However, there are instances where you need to create your own protocol.
Yes.
Can you talk a little bit about that?
Right. Like we said, the EUSART has a lot of additional features for other protocols, but we cannot basically include all the protocols in the world in our simple peripherals. But with a combination of our existing peripherals, you can actually create your own data protocol for a customized design.
Okay.
Yeah.
And so you have an example here.
Right. Let's show the example first.
Okay.
Yeah.
So
right now I have this Express board, which has it's called a 4x4 RGB click. And it's using an RGB LED. It's integrated chip. It's called WS2812.
Okay.
Yes, and it's widely used in all kinds of like RGB lightings, like stage lightings or,
Okay.
So I'm gonna plug this in, and this time it's gonna be a little bit shiny.
A little bright.
Yeah.
Okay.
So here's our demo.
So it's
basically it's switching like colors.
Yeah, it's kind of going. There's a yellow, red, blue. You may not be catching all the different colors. But you'll have to
I was
take our
going for
word
like
for
orange, purple, and.
Okay.
Yeah.
Well, your yellow is maybe my orange.
Because
I got
so
bad
basically,
eyes.
the principle of RGB lighting is you mix 3 components together. It's red, blue, and green.
Right.
And, you
depending
mix them
on
together.
what value you set R2, G2, B2, it's going to change the color.
Yes. Like my orange is like half red and half yellow.
But there's a problem with this particular device. And what is it?
So I'm going to show it on my screen. So here is a typical usage of this kind of application where you have a licenser, but in this case we don't have it in the demo. But basically you're driving this matrix of lighting components. And if you break that down, it's a string, of the pixels. Each pixel is one WS2812 or 11. They are pretty similar. And then.
But you have to communicate.
Yeah, you have to communicate through digital line, and they
a
have
single line.
Right, and they have this single line communication protocol they designed.
That they created. It's a custom.
Yes,
So
yes, it's a custom.
not
So
only they use this.
right,
So,
right.
Okay.
And for each color, it's 8-bit of data, so 24-bit for each LED, I would say.
Okay.
So basically, how you drive the well, I'm gonna basically.
While you're doing that, I think there's a question in the booth.
Hey, Mark. Yeah, we got a couple questions, couple really good questions. First from Jorge, can you address the LEDs individually, or is it the same data for all the LEDs all at once, like Daniel was showing in his demo?
So you can. So basically, the LEDs is implemented as a string. So you light on. So in your data, you're always sending your data for all of your 16 LEDs all together. But
so if you want to get to this LED, you have to shift it through all the other LEDs.
Yeah, you have to shift through all these. But you can just send empty commands so you can just light up one of the LEDs in the middle.
Okay.
Or if you just want to light up the first LED, it's just one, just 24 bits of data.
But if it's 5 LEDs in, you have to shift through 4.
Yes.
Okay.
Yes, exactly.
And Daniel, on that demo, I believe I believe we have an Express example or something like that. We can post this in the show notes.
Right.
But that actually does a bitmap for you, so that all you have to do is put in the individual images or shapes.
And that's for an 8 by
like
32 display, which is
Right.
Yeah.
And we also have a Express example for this particular RGB click.
Oh, okay, cool.
And it has different modes, and it also has a bitmap. So all you need to do is go there and tweak their routines a little bit to create your own patterns over there.
And you know, traditionally to do this, Daniel, it was, and I think you're about to talk about that, but this was just implementing this protocol consumed a lot of CPU resources,
Yes.
which required that you couldn't use this on a lower end 8-bit device.
Right.
Correct?
Yeah, I'm going to talk about
Yeah,
that
let's
in a
let's
minute.
take a look at that.
Yeah. So I have this data sheet for the WS2812 opened, and if I scroll down, you can see the actual timing here. So it's pretty like a precise timing control for their protocol, where it determines a certain amount of on time and off time for your logic 1 or 0.
Okay.
And so if
If
you
you did
were
that
to
in
do
code?
it in code, it's a lot of code, because what we call the bit banding is
Bit banging.
yeah, it's using pure
Peripherals replace
software.
that.
Yes, yes. And you can see this is my routine for writing that code, and you're setting the output high for several seconds and setting the low for several seconds. And as you can see, it's only like 500 nanoseconds. So it's pretty short amount of time, and you need to keep your CPU operating all the time. That means by driving just one LED, you're consuming the full power of your CPU for the full resource.
Never
and
mind.
You cannot do anything else.
Never mind 8 by 32 or.
Yes.
Yeah,
This is
okay.
the 4x4, so it's
Yeah.
like 16 times 24 bits amount of data you need to transmit at one time.
Right.
And that's a lot.
So how did you actually get this to work on the PIC?
So what we do is remember we talked about the CLC, the configurable logic cell last time for the logic outputs.
And for viewers who may not know what the configurable logic cell is, it's a peripheral that has logic gates in it.
Yes.
It has latches. It has sequential logic in there, which may look like a very basic peripheral, but here is one of the powerful aspects of it.
Here's actually a real-world application in there, and we have the application node online, so you can check the detail on that.
And that's what the AN number is. So if you go to Microchip's website and you go into the search field and type in AN1890, it should pull up that app node for you.
Yes. So what we do here is combine a standard communication peripheral, which is SPI, with the PWM, with some kind of logic operation here for your CLC. And as you can see, if I apply this kind of logic, I can get the output signals as I want to.
Right.
Yes.
And this again is completely detailed in the.
Yes, in data sheet.
Okay.
Sorry, the application.
The application
nodes.
node. Yeah.
Yes, and basically you can see on my SPI data, as long as it's a 1, then I'm outputting a 1 in my customized data protocol. So it aligned with our SPI output.
So if we boil this down, essentially what you're doing is instead of using that elaborate software routine to create this custom single line serial communication, you've created your own peripheral by combining some peripherals using the configurable logic cell.
Yeah.
And now all you have to do is pass your bytes of data into that peripheral, into the SPI specifically, and then that will output that data in the format that is required by these WS2811 or 2812 devices.
Exactly.
Oh,
and
wow.
with this combination of our 3 peripherals, I actually create my own peripheral. We can name it WS2812.
Yeah.
Yes. And if you look at, so I'm going to show you guys the project
Inside
here.
of the code configurator.
Yes.
And you probably can't name it WS2812. I'm sorry.
Probably can't.
No, we
cannot.
wouldn't do that. 'Cause-
So takes a while.
Takes a second to load up.
Yeah.
Okay.
And then you can see the 3 peripherals I'm using. This is, so MSSP is essentially an SPI.
Can you go back to that CLC screen?
Yes.
So again, like the code configurator just puts this into perspective as gates. If you were programming this in software from scratch, you would have to go into the data sheet, figure out registers. Each one of those connections is a different register. The way you set the output, so there you've got the output of your OR gates negated, so that's a bit in a register somewhere. So if you looked in the data sheet, you'd see just a series of registers, whereas this presents the peripheral in a more visual way.
Actually, we also have the register view for the MPLAB code configurator, where you can actually see a datasheet fashion of writing the registers.
Okay.
And you can see these are the inputs and outputs of your CLC gates. And that's a lot that you need to configure.
Okay.
Where in your easy setup, you can just configure the gates here. And you can select different kinds of combination of logic here.
What I like too is the pin manager below, where you can see all of those little blue boxes are essentially pins on the microcontroller that you can connect these various signals to.
Yes.
And that's the PPS, or the peripheral pin select.
As we talk about the PPS, that's the PPS. Like I can, basically, my output can be routed to different pins by just clicking.
Or multiple pins at the same time.
Yeah, exactly.
Nice. Okay.
So if I go to my code, all you can see here
you're just
I
see.
really
You're just writing to the SPI.
Yes.
Your
So-
red value, green value.
So
blue
these
value.
3 lines are essentially our 24 bits data output for one LED, and as you can see, I'm writing a loop for 16 times. That's why all my colors of the lights are the same.
I see.
Yes. So it's as easy as that.
Because there's 16 lights.
Yes.
Okay.
Yes. And
very cool.
Yeah.
So there you go. So in this kind of output episode, we covered a few things. We covered the general purpose input-output. There's more than meets the eye to this peripheral, and a lot of useful capabilities on there. We looked at different ways to manipulate PWMs or square waves, how to improve the resolution, how to minimize the amount of code you want to write. That very well translated into the communication protocols, where we saw that we have a variety of the standards, but you can also, you're not limited by that. You can, if you are presented with a custom protocol, maybe you can make your own peripheral with that.
Yeah.
That's pretty much all we have out here. Matt and Wayne, is there anything to add from the booth?
Hey guys, thank you so much, Mark and Daniel. We will be pulling our winners now, so that's exciting. Obviously, if anybody else has any questions as we're doing this, please feel free to throw in any last-minute questions or things like that. And then
before we do that really quickly,
yes,
I'm going to throw it back to Daniel. And Daniel, I want you to actually show us what we're giving away, since you're actually
good call.
holding the board.
So I'm actually holding the board. So this board is called Xpress board, which is essentially this. And then we're also giving away this 4x4 RGB click, which is what I'm demoing here. And you can go to our Express site. There's tons of code applications, code examples for it.
And that black header you can actually plug in any click to as well, right? So if somebody
Yeah.
wants to do an RGB application and then move on from there, it's as simple as just clicking it in.
That's right. So you actually get to for those 5 of you who are lucky enough to win, you'll be able to actually do this demo gratis, I guess.
Exactly.
All right, ready?
Cool. So yeah, so we have the 5 winners, and I'll move this over here so you guys can actually hear them. Our first drawer was, and I will probably butcher this, so just forgive me now, Kumaraswamy Gaviyappa, or something close to that. Welcome, you got a free Express board and an RGB click. So, and then just a quick side note moving forward. We are going to go ahead and throw up that email, which is livestream@microchip.com. And that's how you're going to get us the information. And what I need from each of you is your name, your full name. I need your shipping address, because that's how we're going to get the board to you, obviously. And then we also need your phone number included in that shipping address. That's something, as we work with the shipping company, that they always request. So if you can send me those 3 things, we'll get those boards out to you as fast as possible.
You know, I have to congratulate you on the fact that you've gotten the email address correct.
I have.
Good.
If you've been following along in past live streams, that has not been my strongest moment.
It's kind of the weak point of the whole stream, I think.
It is probably the weakest part. All right, our second winner is Luis Cajuana.
Second weak point.
Yeah, names are my other weak suit. Luis Malave, Mario Camarillo, and Craig Potter. Craig Potter, you had some great questions, so appreciate that. So those are our 5 winners this time. Once again, shoot me your name, your number, and your shipping address to livestream@microchip.com.
Yeah, I'd like to give an honorary shout out to Jorge. We would have chosen you as a winner, Jorge, but we actually know you have all the boards because we met you in August. So,
yeah, and then
also shout out to our moderators.
Yeah, we've had some great moderation today. Thank you, Ashish. Thank you, Mamoon. Thank you, Rachel. Actually, Gerard got one more sweet question. Did Garrett answer it?
And thank you, Garrett.
Yeah, Garrett Scott has been a great contributor to the discussion as well. We've got Luis Edgenar has asked some great questions. Svetloslav has as well. I'm just gonna keep.
You're just gonna stop right.
I'm gonna keep trying. I'm gonna learn them. We really do appreciate you guys wrapping up. Last thing. If you guys have anything that you would love to see us do live streams on, anything,